Let's suppose we're writing a console program in C on a PC. And let's suppose we add in some printf and scanf functions like this. Let's run this. You will notice that the printf function sends its output to the computer screen, and scanf takes its input from the computer keyboard. Also, printf allows us to easily format the output. For example, it gives us an easy way to print a number in hexadecimal. That's all well and good, but what if we try using printf and scanf on a small microcontroller, such as the AVR ATmega 1284? There is no screen connected to this microcontroller. That is, unless we somehow wire one up to it. So, where would printf send the data? Also, there is no keyboard connected to this microcontroller. That is, unless we somehow wire one up to it. So, where would scanf get its data from? These are all good and valid questions. How do we use printf and scanf on a microcontroller that has no operating system installed? What if we want to send our printf and scanf data to and from the UART, or any other peripheral such as the SPI bus, or maybe we want to use a custom parallel bus? That will be the subject of today's video, so stick around and I'll show you how I do it. So first, what is the purpose of this video? Why am I showing you this? Well, in some future videos, I'll be using the printf and scanf functions with microcontrollers. For example, I'll make a video showing how to program flash memory chips, and I'll be using printf and scanf in that homemade programmer. Separating this info into its own video will help make those videos shorter. Now, before we get started, I just want to point out that the info I will be providing today is specific to the AVR new C compiler. Specifically, I will be using Atmel Studio 6.2 with the GCC new C compiler installed. I cannot guarantee that any of this will work with any other compilers or microcontrollers. With that said, let's talk about printf and scanf. Where do they send and receive their data? The printf function uses the standard out stream, and scanf uses the standard in stream. On a PC, they would be initialized to send data to and from the screen and keyboard. But on a bare metal embedded microcontroller such as the AVR ATmega 1284, there are no applicable devices. So these streams are not pre-initialized at startup. We need to initialize these streams ourselves. Today, I'll be directing standard out and standard in to and from a UART on an ATmega 1284. But you can use this same concept to direct those streams to any other output and input devices. So, to get started, let's create a function that is going to initialize the UART. The ATmega 1284 has two UARTs, UART0 and UART1. I'm going to use UART0 for this, but you could always rewrite the code to use UART1. I'll put this into a file called uart.c. This function will take as its input the baud rate we want to use, and a pointer to a file structure that we will use for the new stream. I'll place the function prototype into a header file named uart.h. So first, I want to calculate the value for the baud rate register, UBRR0. And if we look at the data sheet, we can see that this is the formula. So I'll just put this into the source code like this. I'll define f_CPU in a file named init.h. And I'm using a clock frequency of 20 megahertz. Now, the problem with this is that by using integer math, everything to the right of the decimal point gets truncated. So we can use the round function like this. Notice that I'm leaving all the various calculations in here. I'm just doing this so I can demonstrate these calculations before deleting all but the final one. Since I'm using the round function, I'll need to include the math.h file. But this still won't work correctly since the integer that we're passing into the round function is already truncated to the right of the decimal point. So we'll need to turn part of this into floating point like this. That'll promote the entire calculation to floating point, so the round function will work correctly. But we can actually do this calculation without using the math library or any floating point values. To accomplish this, we just need to add 1/2 to the calculated value, and then we can just naturally truncate everything to the right of the decimal point with integer math. Now, you might be thinking that 1/2 is actually a floating point value. Well, yes, but we can represent it as integer math. This is how I'll do it. I'll add 1/2 to the end like this. -1 plus 1/2 is -1/2. 8/16 is the same as 1/2. Now, I'll multiply the whole thing by 16 and divide the whole thing by 16. And that's our final formula, with no floating point or functions from the math library. Now, I'll just create a quick function call to test this out. I'll use the values of 119,047 and 119,048, since they will produce just over 9.5 and just under 9.5 respectively. So 119,047 should give a value of 10, and 119,048 should give us 9 after rounding. I'll start with 119,047, which should give us 10. But the first one gives us 9, which is incorrect. The second one gives us 9, which is also incorrect. But notice that the third and fourth assignments give us the hexadecimal value of A, which is 10 in decimal, so these are correct. Now, we'll try 119,048, which should give us 9. And all 4 should work for this, since this only needs to round down, and the problem comes when rounding up. And they all calculate to 9. So the last 2 assignments work, and we could use either one, but I'll choose the last one and delete the rest. This way, we can get rid of this math.h include. Perfect. Now, instead of passing this calculation directly to the register, I'll put it into a variable named baud register value. This way, I can test it for the maximum value of 4,095 and make sure we don't pass a value larger than that. For example, if we try to set a low baud rate such as 300, then the value will be higher than 4095. Also, I want to make sure that the baud rate isn't too large, so I'll test for that. It can't be larger than 1/16 of the CPU frequency, unless we're using double speed, which I'm not. Now, I want to set up the UART as asynchronous with 8 data bits, 1 stop bit, and no parity. This is actually the default initial setting of the USART control registers when the microcontroller is first powered on. So, unless we change anything, we wouldn't need to do anything further. However, it is possible that some of the registers could be altered before this function is called. So, to be safe, I'll reinitialize all the control registers. Now, for the USART control and status register A, you'll notice that these are the only 3 bits that can be written to. The others are read-only. Since all the writable bits are 0, I'll just assign a 0 to this register. We don't need to worry about this bit being 1, since that's read-only. We'll take care of register B in a bit. The USART control and status register C has these 2 bits set by default, so I'll set those. Now I'll enable the transmitter and receiver of the UART along with enabling the receive interrupt. This will take care of our final control register B. You can read more about the USART registers in the ATmega 1284 datasheet if desired. Now we just need to enable global interrupts and specify our interrupt handler. We'll need the interrupt.h file included for this. This will be my interrupt handler. I'll just take all the input and throw it into a circular buffer. I'll be using these circular buffer functions that I created in a past video. I'll put a link in the description to that video. I've created these simple circular buffer functions in a file called circular_buffer.c. I've made a cbuffer initialize function, which just makes sure the buffer is empty. I've also made a cbuffer put function, which places the data passed into it into the buffer passed into it. Then there's a cbuffer get function which returns data from the buffer passed into it. And finally, there's a cbuffer data available function which just returns the number of bytes stored in the buffer that is passed into it. And all the prototypes are in the circular buffer header file, along with the structure for the buffer. I'll just initialize the buffer in the UART start function, in case we ever stop and restart the UART. Then we can be sure there is no data left over in the buffer. Now I'm going to finish up the UART start function. What we need to do is to redirect the standard out and standard in streams to and from our own functions, which we will create shortly. So first, I'll make sure we were passed a valid UART stream. Now I'll use the fdev_setup_stream function to set up the new stream to use our own functions. I'll call my new functions UART0_send, which will be used for standard out, and UART0_receive, which will be used for standard in. And since I'm adding both a send and receive function, I'll set this up for both read and write. Instead of using the fdev_setup_stream function, I could have used another function called fdevopen, but that function requires malloc, and for a microcontroller with little memory, I prefer using fdev_setup_stream, which doesn't dynamically allocate memory. Now we just need to set standard in and standard out to our new stream like this. Lastly, we just need to write our new functions, UART0_send and UART0_receive. Here are the prototypes for these functions. The send function will take the data to be sent along with a pointer to the stream. It will return a 0 if successful. The receive function will take a pointer to the stream and return the data being received. Bear in mind that you don't really need to do anything with these pointers to the streams in either function. They're just part of the function calls. Now let's create the empty functions. You can set these functions up any way you'd like. They don't have to use the UART. You could send and receive data from anywhere, but then you'd probably want to rename these functions so that they're not named after the UART. Let's tackle the sending function first, since that is probably the easiest one. I want to wait for the transmit buffer to be empty, and then place the data into the transmit data buffer register. This will send the data out the UART. Then I'll just assume the operation was successful and return a 0. Now, I'm going to customize this to my own taste and send a carriage return whenever we send a line feed. You can customize your own code any way you'd like, and you could add in some error checking. Now the send function is complete. Next, I want to write the function that will receive data from the UART and send it to the standard in stream. Now, we could just take the data that was placed into the UART buffer and return that, but you'll notice that if we go back to the program I wrote on the computer and run it, the input allows us to use backspaces to correct mistakes before the input is sent to the scanf function. This is referred to as a canonical input mode. I want this same functionality in my code. So here's how I'll do it. I'm going to create a little one-line buffer that can hold up to 256 characters. Actually, it'll be one less due to the way I'm using the right index, but 255 is good enough for me. I don't think I'll ever need an input of more than that. The write index will be initialized to 0 and will point to the next location to write data in the line buffer. The read index will be used to point to the data being read out of the line buffer. The purpose of this line buffer is to allow the input to be buffered and altered with backspaces until a carriage return or line feed is encountered. Then I'll just create a variable to hold the character or data that is being received. Now, if the write index is 0, that means our line buffer is empty, so we'll fill it up until we encounter a line feed. I'm going to wait for data to be received and then get that data from the buffer. Remember that this data is being received from the interrupt handler that we wrote. Now I'm going to create a switch statement and treat different characters to my liking. You can customize this however you'd like. So if I get a line feed, then I'll add that to the buffer as long as there is something already in the buffer. Now I'll check for carriage returns, and I'll let that use the same code as the line feed, so I won't add a break. I'll change the carriage return into a line feed before storing it, and I'll echo a line feed to the output. This way, if we're using a terminal program, such as TeraTerm on a computer to talk to the microcontroller through the UART, we can handle the enter key on a keyboard, since by default it will send a carriage return with no line feed. You can set up TeraTerm to send a line feed also, but I'm not setting it up that way. Now, for the default, I'll echo the rest of the characters out the UART and store them in the line buffer. The echoing is optional, and you could always write the code such that all of this is customizable. After we filled up the line buffer, then I'm going to set the read index to 0 so we can start returning the line from our function in a first in, first out fashion. But wait, we haven't handled backspaces yet. For that, I'll create another case statement. We'll make sure there is data in the line buffer before we attempt a backspace. If no data has been entered, then there's no backspacing allowed. I'll simply echo the backspace and then decrement the right index. Also, there's one more small case I'd like to handle. I want the user to be able to enter a Control-Z. This is ASCII code 1A in hexadecimal. I want that to return an end-of-file error. We'll write that to the line buffer and exit the do-while loop when it is encountered. We're almost done. We just need to return the characters in our line buffer now. So I'll just use the read index to take characters out of the line buffer and increment to the next location. Once the read index is equal to the write index, we're done reading from the line buffer and we can reset the write index. And of course, we'll return the character that we read from the line buffer. That's it. We're now ready to use printf and scanf with the UART. So let's go to the main function and declare the UART stream and start the UART with, let's say, a baud rate of 115.2. Now let's add the same printf and scanf code from the initial program at the beginning of this video. And I'll put it into a loop. Now if we compile this, then we should be ready to program it into an ATmega 1284. Let's breadboard the microcontroller up really quick. Here's the schematic. I'll just connect an FTDI USB to UART cable up to pins 14 and 15 of the ATmega 1284. The orange TDF wire of the FTDI cable connects to RxD pin 14, and the yellow RxD wire connects to TDX pin 15 of the ATmega 1284. Now I'll program the microcontroller and start up TerraTerm and see if this works. And there you go. Both printf and scanf work with the UART on the ATmega 1284. If you created these UART files, you may want to store them away for use in future projects. Well, I hope this video has been helpful to many of you, and I look forward to creating more videos in which we use these functions in future projects. If you liked this video, then please peck at that like button and consider subscribing if you haven't already done so. Thanks for watching, and I'll see you next time, right here on Dr. Play.